We left off talking about what chemistry was and measurement, and using this idea of the macroscopic properties of something to tell us something about what's going on at the microscopic level. So let's get into a little bit deeper and actually talk about matter itself. Most of what we see around us is a mixture composed of many different parts. Almost everything you see around you consists of a mixture. A classic example is something like sand. If you actually look at it, you'll see that it's more than one component. So mixtures come in a number of different categories, and we can use the properties of a material to classify it. Properties fall into a number of different categories as well. So this is about categorizing. There's two types of properties: intrinsic properties and extrinsic properties. Extrinsic properties change with the amount of material. Extrinsic properties are things like mass, volume, things that we usually go out in the lab and measure. They really fluctuate depending on how much material we have. And they're not really as interesting as for us. What we often care about more so are the intrinsic properties, those properties that don't change with how much material there's present. And these properties come in a number of different flavors. One of them is the physical properties, which are those properties that we can measure without actually damaging or destroying or changing the material. By that I mean we can get it back. A good example, this is like boiling point or melting point. We take some ice and we melt it. It melts at 0 degrees centigrade, freezes at 0 degrees centigrade. That's consistent no matter if we have a little bit of water or a lot of water. Other properties, like physical properties, are things like conductivity, or almost anything you can imagine that doesn't change the material or allows us to get it back is a physical property. Contrary to this is things like chemical properties, those types of properties that result in an inherent change in the material such that it is no longer the same compound or substance. A good example of this is something like sensitivity to acid, reactivity towards oxygen. These are what we call the chemical properties. So using these two tools, physical properties and chemical properties, we can start to classify matter. And we can start to classify our mixtures. Most mixtures, again, come in two different categories. Those mixtures, those two categories are what we call heterogeneous mixtures or homogeneous mixtures. A heterogeneous mixture is one where there's an obvious difference between the components. For instance, sand, again, the example I was using. If you look at sand, you'll see that it's composed of many different colored grains. Heterogeneous mixtures have properties that vary from location to location within the sample. So in this particular grain, it's pink. This particular grain, it's black. This one, it's a certain hardness. That one's a different hardness. These represent heterogeneous mixtures. Our homogeneous mixtures are those things that you cannot discern at the macroscopic level distinctions between the different properties. Example like this is, coffee. Coffee without cream. You put in your spoon of sugar, you stir it up. The first taste has the same amount of sugar as the last taste. The sugar is evenly distributed down to the microscopic level. So if you take a small sample, you measure the concentration of sugar, it'll be the same as the next time you run. Air is a good example of a homogeneous mixture. There's no discernible boundary between the individual components until you get down to the microscopic level. Now, a quick test, like a quick way to eyeball something to say whether it's a homogeneous mixture or heterogeneous, is to actually look at it and see if is it transparent, is it uniform. Those are hallmarks of a homogeneous mixture. Even materials that are not transparent, things like brass or solutions that may not be transparent visibly, you'll find that they are transparent to other wavelengths of light, like X-rays. So this is a quick hallmark of whether or not something's homogeneous, uniform down to the microscopic level. Now, the properties of mixtures. You take a mixture, you can use your physical properties to take components of that mixture and start to split them into different things. You take this sugar water solution with a little bit of caffeine in it, and you use the physical property of water, its evaporation temperature, boiling point, to evaporate off the water, and you'd be left with sugar and caffeine as a residue in this cup. So with heterogeneous mixtures or homogeneous mixtures, you can use the physical properties to separate them into their components. Now, those components are what we call pure substances or pure materials. They only consist of a single component. If you separate the physical side of them down to the microscopic level, eventually you get to a point where you can't physically separate it into anything new. These are what we call substances or pure materials. Substances themselves also have multiple classifications. So those substances can fall under two different categories. The more common one are what we call compounds. These substances can be altered chemically and separated into components. Now, this is chemical separation. This is realized in the chemical properties, sensitivity to oxygen. For example, you can separate those components into simpler materials. Those simplest materials that can't be separated anymore are called elements. Elements all consist of the same type of atom. We'll talk about atoms in a bit. All elements are the same type of atom. A pure element contains nothing but the same type of atom. Now, if you start taking those elements and chemically combining them, you start to form what are called compounds. Compounds consist of more than one element bound together in some fashion. And by bound, I mean the elements are chemically held together in some way, using what we classify as a chemical bond. This is as simple as these are the simplest components that you're going to see that all have the properties of a given compound or element. This slide just summarizes what I was just saying. We have matter, and that most of matter, what we look at is going to be mixtures, and mixtures are either heterogeneous mixtures, which have lots of different components, and we can recognize them as heterogeneous by the way they look or the way their properties vary from location to location, or homogeneous mixtures, which are uniform down to the microscopic level. Again, macroscopic down to microscopic. We can then separate these mixtures into pure substances based upon their physical properties: boiling point, melting point, evaporation, whether it dissolves in water. If we had a sand-salt mixture, we could dump it into water, the salt would dissolve, the sand would be left. So based upon the physical properties of the material. Once we separate them, we're left with, as far as we can separate them down, the pure substance. Those substances fall into two classes: elements, which only consist of one type of atom, or compounds, which are multiple types of atoms bound together. So all of this is leading up to our periodic table, which you should have already started studying and memorizing. Remember stuff we were supposed to memorize, go back to the week 0 stuff. All right, so each of these little letter combinations represents an element, a pure substance consisting of only one type of atom that has a unique set of physical and chemical properties. And what we're going to talk about is how these change. Now, chemistry is not a new science. No. It's been around for a while, and one of the central tenets in chemistry deals with Dalton's atomic theory. Now, this is a theory, early codification of what chemistry is about. You don't need to memorize these. You know, I'm not going to say on the test, we'll list all four of Dalton's atomic theory. But you should be able to rationalize what's going on in a chemical reaction based upon these central tenets. So let's just talk about them real quick. Dalton's atomic theory is really simple. After extended observation, Dalton came up with this idea of elements. All right, this is sort of novel. Elements are composed of extremely small particles called atoms. We take this for granted now, but in 1808 it was kind of a novel concept. All of the atoms of a given element are identical. Same size, mass, and chemical properties. Actually, this turns out to be a little bit wrong, and we'll talk about that. But the atoms of one element are all different from the atoms of another, and there's something different about them, and we can use that difference to get at what makes them behave the way they do. Now, compounds are composed of atoms of more than one element that are come together, and in any compound, the ratio of the atoms to any other element present are always going to be a simple integer, or a fraction, depending on how you look at it. Basically, what this boils down to is that compounds always have whole atoms, and that the atoms are always bound together in groups. And lastly, when you do a chemical reaction, the only thing that changes is a separation or combination or a rearrangement of atoms. What you start with is what you end with. There's no new creation or changement of atoms. Now, this is distinct from radiochemistry and nuclear chemistry, where there's a nuclear reaction that takes place that alters the number and type of element. This doesn't happen in chemistry. So for the most part, we're not going to talk about nuclear reactions, except when we talk a little bit about the history, which will be the next little